Welcome to this RISE 101 module number 3. My name's Griffiths Atungulu. I'm the director of the Arkansas Rice Processing Program. I'm an associate professor and an agricultural engineer. My area of specialty is in grain processing and post-harvest systems engineering, and I'm housing the Department of Food Science with the University of Arkansas System Division of Agriculture. In this module number 3, we want to look at some of the concepts of psychometric and how we can apply that particularly in rice drawing. Some of the things that we are going to go through include understanding what psychometric charts are, understanding some of the most air properties that are found in psychometric charts, and then kind of go through a few problems here and there to see how we can use psychometrics in combination with some of the concepts that we have learned to do some drying calculations for rice. Now, to begin with, I want to start by saying that air is a mixture of gases and water vapor. And psychometrics is that study that helps us to understand these thermodynamic properties of the gas and air vapor mixtures. Now, psychometric charts have been developed and available for us to kind of see the interactions among these physical properties, and this is very, very vital and important for us, especially when we are doing some drying problem calculations. I want to start by describing some of the parameters that you typically find in a psychometric chart and that are very relevant to us when we are dealing with rice drying. The first parameter is the dry bulb temperature. This is the temperature of moist air using just an ordinary thermometer. And the most common units that we are familiar with are degrees Celsius and degrees Fahrenheit. We can convert one unit to the other using some of the formula that are presented there. We can also express some of these units in Rankine or Kelvin. The other parameter that I would like to describe is the wet bulb temperatures. Slightly difficult concept to understand, but very, very useful to us when we are dealing with rice drying. The wet bulb temperature is measured using a thermometer with a bulb that's wrapped with a wet cloth. So I want you to imagine you have a thermometer, and at the tip, at the end where we have the sensor for the temperature, you wrap that with a wet cloth, or sometimes called a wick. And the wet bulb temperature represents the lowest temperature that can be reached under those current ambient conditions by the evaporative cooling that happens on that wet cloth. So this also represents the temperature that is typically felt by our wet skin when we are exposed to moving air. And it's determined by the dry bulb temperature and the humidity temperature. This slide here shows an instrument that we can use to determine wet bulb temperature and dry bulb temperature, and in combination eventually determine the relative humidity of air. You can see two thermometers there. One thermometer on the top has got at its end a wet cloth wrapped around it, and the other thermometer does not have a wet cloth. So the one on the top is going to help us measure the wet bulb temperature, while the one on the bottom is going to help us measure the dry bulb temperature. What happens is when you swirl that thermometer around, when it is wet, you are going to have the air pick moisture from that wet cloth, and by so doing, we go through what's called evaporative cooling, and that evaporative cooling at the end of the day is going to make the temperature on the wet bulb thermometer to be lower than the temperature of the dry bulb thermometer. The next term that I want to describe is the relative humidity. Humidity, just by description, is the amount of water vapor in the air. And relative humidity is the amount of water vapor in the air relative to what it can hold at that particular temperature. And to help us understand that, I would like you to look at this diagram that kind of shows air volume. Imagine this air volume in a balloon, and there's water also in that air volume. And typically those water molecules are dispersed within that volume. Now let's assume that that air is at 30 degrees Celsius. And it has some given amount of water. You can notice that there's still a lot of space in there that could still contain some water. And so that air is not saturated at 30 degrees Celsius. The relative humidity in this case is 28%. And so as we continue reducing the temperature, you can see the volume is also reducing, and the capacity of that air to carry water also reduces. So does the relative humidity increase. So at 20 degrees Celsius, the relative humidity is at 52%. And as we continue reducing that temperature all the way to 10 degrees Celsius, we reach a point where that air volume cannot contain any more water. So at that point, we say that that air is saturated. It cannot contain any more water, and the relative humidity is 100%. The next terminology, very simple to understand, is the humidity ratio. This is the ratio of the mass of water that is contained in the air per unit mass of the dry air. So again, the common units for this are kilograms of water per kilogram of the air. That's in the SI units. And it can also be expressed as the grains of moisture per pound of dry air. This is the British unit. And in this case, 7,000 grains is equivalent to 1 pound. A grain here is a unit, and it's not grain as we would understand it for food. This slide here is helping us understand another property, and that's the dew point temperature. And I would like to start by kind of explaining that in this diagram, the vessel volume here represents the air molecule volume. So on the rightmost, you see a vessel there which is 20 gallons, and let's assume that is the air molecule volume. And inside that volume, we have water that is dispersed in vapor form. And so that is at 70 degrees Fahrenheit, very high temperatures. So the relative humidity in that case would be 8 gallons of water divided by 20 gallons, which is the vessel volume. That's about 40%. Now, as you reduce the temperature and maintain the same amount of water inside, you notice that the vessel volume reduces. And as the vessel volume reduces, the relative humidity increases. All the way to about 45 degrees Fahrenheit, we have 8 gallons of water in a vessel volume of, that is 8. At that point, again, we have reached a point where that air cannot contain any more moisture, and therefore it's going to spill out moisture. At that point, we say that we have reached the dew point temperature of the air that was initially at 70 degrees Fahrenheit. So as air cools, its water holding capacity decreases. The temperature at which it can no longer hold water is the dew point temperature. The next item or terminology that I would like to describe here is the air-specific volume and the air enthalpy. And this diagram here is to help us illustrate that concept. So I want you to imagine a piston cylinder arrangement, and inside that piston we have air, basically water and other gases together. As I move that piston up and down, I'm able to change the volume within that of the air, but I'm maintaining the amount or the mass of that air. So typically, the way we describe the specific volume is the volume of that air per unit mass of that dry air. And the units are in meters cubed of air per kilogram of the dry air, or feet cubed of air per pound of dry air. And the specific enthalpy that is associated with that can also be described as the heat content of air that is having a unit mass, that is in that unit mass of dry air. And the unit that's associated with that is the kilojoule per kilogram of dry air, or the BTU per pound of dry air. Next, I would now want to bring all this together in what we call the psychometric chart that now help us to understand the interrelationship among these parameters as we go through various processes, whether it's heating, whether it's cooling, whether it's humidification or dehumidification. And in this chart here, we have all these parameters represented. We have the dry bulb temperature on the x-axis. We have the humidity ratio on the y-axis there. And we also have lines that represent the relative humidity, and we have lines that represent enthalpy, lines that represent the wet bulb temperature, as well as dew point temperatures. And so once we know some of the parameters, and we are able to locate the process on the chart, we should be able to find all the other parameters. And we'll describe that as we go along in this lecture. To begin with, let's assume we are having air that is being cooled, and we know its temperature, and we know also its humidity. If it's being cooled at, if it's being cooled at a constant humidity ratio, it will follow a line towards the left, as you can see. And as it does so, the wet bulb temperature will change as well as the humidity. In the next slide here, we are showing the same thing, but in this case, we are heating this air. And so we are moving from the left to the right. As the temperature increases, you can notice that the humidity of that air is increasing. The enthalpy is going to increase. And many other parameters like the specific volume are also going to change. Sometimes we are interested in adding moisture. And if we are adding moisture, we are going to have to follow a line, as you can see in that diagram, where our humidity is going to increase. So we are increasing humidity at a constant temperature. In other cases, we are dehumidifying. And in this chart, in this diagram here, I'm showing all this put together where we have cooling, we have humidification, we have heating, and dehumidification processes. And so once we know one point on the psychometric chart, we can follow any other processes that air would go through in a typical drying, cooling, aeration scenario. So just to summarize kind of how we go about that, there are steps that we can use to determine air properties. The first thing is two values of the air characteristics should be known. Then we need to plot a point on the psychometric chart using those two values, and then follow the constant property line for determining the remaining air properties. I want us to go through two examples here to kind of help us appreciate the usefulness of psychometric charts in drying rice situations. Now, in this first problem, air enters rice in a bin dryer at 95 degrees Fahrenheit and 75 degrees Fahrenheit dry bulb and wet bulb temperatures, respectively. We are being asked what are the relative humidity and the dew point temperatures of this air. So as I mentioned, we have two parameters that are known, the dry bulb temperature and the wet bulb temperature. So it's so easy for us to go on a psychometric chart and locate those 2 points. And where they intersect, we should be able to read the relative humidity. And in this example, if you do it right, you'll find that the relative humidity is 47%. And the dew point temperature is 72 degrees Fahrenheit. The next example is going to draw concepts and kind of combine the use of psychometric chart and a concept that we learned in a previous module, and that's the concept of equilibrium moisture content. In this example, a rice farmer wants to dry rice at 19% moisture content wet basis in a bin. The outside air wet bulb temperature is 70 degrees Fahrenheit, and the dry bulb temperature is 75 degrees Fahrenheit. We are being asked what moisture percent can the farmer dry the rice to using the outside air. So to solve this problem, we first of all look at what we are given. We are given the dry bulb temperature, 75 degrees Fahrenheit. We are given the wet bulb temperature, 70 degrees Fahrenheit. So with those 2 points, we can go on the psychometric chart and locate exactly where that point is. Once we locate that point, we should be able to know very many other parameters. For example, we can know the humidity ratio, the enthalpy, and so on. But what's very important for us here is to know what the relative humidity is going to be. And so using the psychometric chart, we can determine the relative humidity to be 80%. Okay? Now, once we know the relative humidity as 80%, we now need to combine that with another very important concept that we learned in previous module, and that is the concept of equilibrium moisture. Equilibrium moisture content basically tells us the moisture content that rice will settle at for a given set of temperature and relative humidity. Our problem has told us that we have the dry bulb temperature at 75 degrees Fahrenheit and the relative humidity at 80%. So looking at the equilibrium moisture content chart that we are provided there, and this one it shows this is for rice long grain. If you look at this, we have the temperature on the left side and the relative humidity values on the top. So we would have to look at the relative humidity of 80% intersection with 75 degrees Fahrenheit temperature, and we realize that the equilibrium moisture content of that air is going to be 16.2. And so this farmer using this air is able to dry this rice from 19% moisture content to 16.2% moisture content. And so I'm leaving you here with some references that are going to be very helpful for us to kind of dig deeper and understand a little bit more on some of the concepts that we have covered in this module. And with that, I want to say thank you very much for listening to this module on psychometrics and the applications in rice drying. And I look forward to developing more knowledge together in the next modules. Thank you.